So the next talk will be about typed security, not mistaken by the type security we had at the first talk today. Michael Koppmann, he's also a dear colleague of mine in the pen testing team, and he is also one of the co-founders of sec4dev, and was there when we were sitting at the Weird Developers Conference and think, oh, there are a lot of devs who are interested in security, let's make a conference. That's where you are today. So Michi, he's talking about types in programming languages protect us from doing mistakes, but it also depends on the chosen language, how strict the protection is. And he will talk about and showing you a couple of examples how to encode business workflows and constraints into types. Thank you.
Thank you. Let's hope that technology will not fail me. Looks good. Okay, hi everyone. Are you enjoying the conference so far? Yeah. That's good to hear. Can anybody hear me? Also in the upper stairs? Yeah? Cool. This is my first time speaking in front of such a large audience, so please excuse me if I'm a little bit nervous. But after this talk, there will be the lunch break, so let's get started. So today I will tell you a little bit more about typed security and the power of strong type systems, and how you can structure your applications in a way that you can prevent some security classes by design. I hope you're not afraid of code snippets in languages that you don't know, because there will probably be some of them. So let's begin. I'm Michael Koppmann, like Steffi introduced me. On the slide, you can see how I looked like before the pandemic. I'm a penetration tester at SBA Research, and I'm also working on some software projects too. And during my work, I see a lot of code of questionable quality, and I see the same mistakes repeated over and over again. So that was one reason why we founded the sec4dev, to provide you with practical and valuable tips that you can then take with you and improve the quality of your software. At least we try. So the whole idea for this talk came when I learned about domain-driven design. The term was originally coined by Eric Evans in this book. You may have heard about it. It's also known as the Blue Book. Guess why? And it was written almost 20 years ago, but many of its wisdoms are still relevant today. The core ideas of domain-driven design are that your code and the structure of your code should match your business needs and the business domain. It teaches you to focus on your core business logic and how to design your programs in a way that technical details stay abstract and can be replaced later on. While collaborating with your business experts and domain experts, you develop an ubiquitous language that every person in the project involved can understand. So no abstract singleton proxy factory beans allowed. Many of its concepts got popular over time, like entities, objects with an ID and a life cycle, value objects, which are immutable, data only and with no behavior, aggregates, which are protecting invariants across multiple entities, bounded contexts, the logical components that your application is made of, and repositories that help avoiding polluting your business logic with technical details for persistence. Now, let's add types to the equation. So, object-oriented programming combined data and behavior, but it was originally meant to just simplify maintenance. The ideas that types or classes can also be used to encode business rules is rather new. There's this catchphrase, make illegal states unrepresentable, and this means that you design your data types in a way that invalid combinations are just not possible. So let's imagine that you have some configuration tool with 3 settings, and you could use 3 booleans for that, right? But you know also that some combinations don't make any sense. So if you have option A, B, and C, and option B depends on A, it shouldn't be possible to set B but not A. But the Boolean-based design doesn't prevent that, so you have to write runtime checks for that and write unit tests to cover all combinations, and that's a source of errors we want to avoid. We can build further on this and even prevent some some vulnerability classes, and let the compiler help us in this case. You will see some examples for that later on. It's beneficial that you use immutability to avoid doing the same checks over and over again. So if you have an immutable value, it's set when the variable or the object is created and cannot change anymore after that. And if you design your application in a way that it doesn't allow any invalid input arguments or state, then the compiler will force you, will guide you through your programming experience, and it will prevent you from accidentally doing the wrong things. So you don't have to write tests for that, and you don't have to write runtime checks for that. So that's something we absolutely want as lazy programmers. A little disclaimer here. The techniques that I'm going to show you can be used in all programming languages, especially the more general DDD patterns. But some make it easier than others, and especially statically typed languages can get the most out of it because you can just pull all these errors into your compile step so your program doesn't break when your customer is using it. Still, even when you're using dynamically typed languages, some of these tricks can still help improving your code quality. A powerful type system then, in addition, allows you to put even more constraints and rules into the type system, so more bugs than can be caught automatically. Two features that are very nice to have, but are still rather new in the more mainstream languages, are sum types, also known as tag unions, and pattern matching. You can imagine, for simplicity reasons, that sum types are like very powerful enums, and pattern matching is a very powerful version of a switch case statement. Here's a small list of languages which provide a very powerful type system, and I will use some of them because they allow me to present some ideas in a very concise way. But if you're not, I will explain all the code snippets so you don't have to know the language to understand the examples. The most popular ones on that list are probably TypeScript, C#, and Java. TypeScript has sum types, but no pattern matching. C# has pattern matching, but no sum types. And Java 17 has both, but I assume that most of you don't know them already because it's a rather new feature. So I assume that all of you know what null, okay, so good. I assume that all of you know what null is and the infamous null pointer exceptions that come with it. Tony Hoare, who introduced this idea and who brought us this gift, called it this billion-dollar mistake. But what exactly is the problem with null? The problem with null is that it's implicitly a member of every type, so it can be always returned. That makes it very hard to provide some reasonable advice. So you basically have to do checks for null all the time. Some languages decided to never introduce null and modeled the absence of a value explicitly. And Java and others since then have adopted this idea. And with that, it's time to see the first code snippet. In this case, it's in Java. In this example, we work with a map, so a key value structure. And map provides a method called get. And you give it a key, and you will get back the value stored in this map, but only if the value exists in the map. If it doesn't, you will get a null. And we want to avoid that. So the first function builds a safe wrapper around it. This lookup function calls the get function from the map, but then returns an optional. And optional is a class that represents potential failure. It can either be present or empty. This means that a compiler can then force you to provide checks for empty and therefore protect you against any null pointer exceptions. But in Java, it has to be backward compatible. There are still many places where null is leaking, but other languages that really enforce this have a big other benefit. When something is not declared as optional, you really know that the value is here, so you don't have to write all these defensive programming techniques, and your code is much cleaner. On line number 5, you have this get contact description or default, which then uses this lookup function, and it receives a name and a phone book, so with strings and as a key and its values. And first we call the lookup function and get back our optional of string. But we can't just return this value because our function says it returns a string and not an optional of string. So first, we somehow have to unwrap this value, but unwrapping it sounds like, okay, we just replace this with another type of null check. But optionals have this very nice interface that you can basically use them similar to lists. So we have this map function where we can apply some lambda, which is only applied if the value exists, and if it doesn't, the map just does nothing. And with this or else, we can provide some fallback case that gets executed if the value was nothing. And with this, we can see that the compiler in this case helped us checking for this explicit case where we have to provide a value if the value is here and some fallback value because our types just say you have to do this. Did you know that using the same basic data types over and over again for everything is an anti-pattern? It's called primitive obsession. The problem with basic data types is that they do not enforce any constraints on the data. So if you generate UUIDs but store them as a string, then someone could just manipulate them, and they're not valid UUIDs anymore. So storing them in a UUID type helps because the class can then protect the access to it and enforces some constraints on how you can manipulate this UUID. But using UUIDs for everything has still the problem that you can mix them up. So in the next example, it's in C#. You can see I wrote a simple wrapper around the GUID class, which is the built-in UUID class in C#. And it's a record and immutable, so a value object in DDD speak. And these two methods are just for easy conversion between this type and the base type. And below that record, you can see the function store payment for user, which expects a payment ID and the user ID. And if we want to call that function then and mix up the two arguments, the program will just not compile because the types do not match. So with only a few extra lines, you can avoid a common source of mistakes. To get a better grasp of modeling concepts and ideas explicitly, let's try to model a contact type. And we will begin with a simple contact type with only primitive types and build on it and steadily improve the design until we have rich domain types that encode business rules. And this time I will use F# for that. It has a powerful type system like listed before and has the huge benefit of running on the .NET platform. So you can easily integrate it into existing projects and access the huge .NET ecosystem. So here we have a type called contact. It contains a first name, an initial name, a last name, and an email address, all strings. And there's also this Boolean flag called is email verified, with a comment that says, if the flag is set to true, then the verification mail was confirmed. But what happens when the mail address changes? Does it stay verified? This thing doesn't say anything about it. So we have to figure this out later. But this is a data type that I see all the time. But we can do better. So now we have three types. Related data is now grouped into their own types. There's a type called personal name, containing the name-related data. And there's this type called email contact info, containing the mail address and the Boolean flag. Contact then wraps those two other types. But this can still be improved because not any arbitrary string is an email address or a name. So let's fix that. The email type now lives in its own file. And this gives us the power to only export certain functions from that module. So similar to public and private functions in Java or C#. And we use this to implement the so-called smart constructor pattern. Line number 1 shows that the type email address is still a string, but its constructor is private. So only functions in this file can access the constructor, but the rest can only use the type. We create two helper functions here, a create function, which will act as our new constructor, and a value function to extract the value from it. F# is a statically typed language, but it can fully infer all types, so I don't have to write them all down here. The value function just unwraps the type, so we can get back the string. But create is a little bit more elaborated. It accepts a string and then uses a regex to check if there is some add symbol in the string. It's not the best check, but we will a better check for that later. This function returns an option of email address. So option is the F# version of optional in Java. And if the check succeeds, then we return some with the email address. And if it fails, we return none. The caller then has to check if this creation was successful or not. As this function is the only way to create something of type email address, everyone is forced to go through this module and through this validation process. If we now look at the rest of our types, some other things have changed too. So instead of string, our email contact info now uses the email address type, and the names have changed too. They also have a smart constructor now, but in this case, they just limit the maximum amount of characters allowed. And initial is also marked as option now to declare that this thing may be missing. We still have this Boolean flag, which doesn't really tell us much about the business process, so time to solve this problem too. The email module was rewritten again, and this time the email contact info is part of this module, and it is now a sum type. So it has two constructors. It's either unverified or, so it's unverified, which accepts an email address as an input, or it's verified, which accepts a verified email address as an input. I get some update notifications here, that's great. The constructor for the email address is public, but verified email address is private. So we again use this smart constructor pattern. With a value function, so that hasn't changed, it's down below here. But we got two new other functions. It's store verification code and verify. Store verification code expects an email contact info and a verification code as arguments and performs pattern matching on the context. So if the contact is already verified, then we just return void or unit, how it's called in F#. If the contact is unverified, then we unwrap the email address and store the address and the code in the database. We then send this code back to the customer so they can perform, click on the activation link or something like that. If we then later call our verify function, this thing expects an email contact info and this verification code. And if the contact is already verified, we just return it back. We have to wrap it with the sum, so all returns in this function return this option. And when the contact isn't verified, then we can use our private constructor here, so we can return this verified email address. Instead of using just some Boolean flags, we now have static guarantees that can be guaranteed by the compiler that all verified email addresses went through this specific verification flow. So nothing really has changed here for the contact type, as it was already using this email contact info. But we have now two new example functions, like send password reset email and change email. And they demonstrate how you can use these types now to your advantage. So send password reset email expects a verified email address. So there's no way to send a password to an unverified email address. Change email is the function that the customers are then calling if they want to change the mail address. It accepts a string, and at this stage, the only available constructor is the unverified one. So there are no more excuses like, oh yeah, the data changed, but I forgot to reset the flag. So this was a brief overview on how you can use types to encode business rules, but there are much more things that you can do with types. So many vulnerabilities exist because they're so easy to make. Let me present some ideas on how you can use then types so that your compiler prevents you from implementing some of the most common vulnerabilities. If you're not familiar with the OWASP Top 10, it's a list of the 10 most common security vulnerabilities in web applications, and they get updated every few years, and the current one is from last year. I picked 3 of them because types can help us prevent them. Broken access control is rather self-explanatory, so an attacker can access data they should not have access to. Injection attacks refers to attacks like SQL injections, OS injections, cross-site scripting. An attacker is providing some input that gets interpreted as code and giving the attacker control over some piece of software. Insecure design, like we heard yesterday, is rather unspecific and can mean many things. As we try to design our system in a way that secure becomes the default, we avoid this vulnerability class. And if you still thought that the latest version is from 2017, I recommend you getting some updates after the conference. The OWASP publishes other top 10 lists too. This one is for API backends, and they share some similarities with the previous one. So number 1 and 5 are broken access control, number 8 is injection attacks, but 3 and 6 are new. So they occur when you expose too much data to your clients or accept too much from them. So let's start then with broken access control and how we can fix them. This time we will see some Haskell code, but fear not, I wrote it as imperative as possible. A company rolled out a new version of the web service, and shortly after, an attacker did some bad things. It's our job now to fix this problem in a way that this cannot happen anymore. So here we have parts of a web controller. We have routes for get, put, and delete. Looks like a simple CRUD application to me. We fetch the current user, extract the article ID from the URL path, check if the user can access or modify this particular article, return 401, not authorized when they cannot, and perform the action when it's allowed. So, question, can anyone see the problem with the code here? Give you 5 seconds. Okay. When the code was rewritten, someone forgot to include the not here. So this, of course, flips the Boolean check. So now legit users couldn't delete articles, but everyone else could. So an attacker swooped in and deleted all the articles. And that's why we have backups. We want to solve this problem once and for all, and types will save us. This is our new authorization module. In the top left, you can see the original Boolean-based functions that do the access check. But the problem with Boolean checks is that they do not prove anything. So once you leave the if-else branches, it's like no check happened at all, and you can do anything in your program again. And we don't want that. We want static proofs that the compiler can guarantee for us, so we don't do the stupid mistakes. At the top right, you can see 3 new types. Access article and modify article both store the ID of an article, and you can see them as some kind of access level. Access token is a generic wrapper. It just takes any type A and wraps it. So for example, an access token access article or an access token modify article. And we have this function called token data, which just extracts the contained value, similar to the value function in our F# example before. On number 3, you can see 2 new functions. We have now get access article token and get modify article token, and they now perform the authorization check, and they do nothing special. They call the old authorization checks, so that's still the same, but instead of true and false, they now return a maybe, which is Haskell's version of option and optional. So a value can either be just or nothing. But what's so special about this? So if we look at number 4, at the module definition, you can see this little dot thing. This just means everything is public and other modules can access the constructor. But if you look closely, the constructor for the access token is not exposed. So the only way to get something of type access token is by calling the functions that are provided by this authorization module. Note that the Boolean-based functions are also not exposed. But that's like only half of the solution here, because the rest of our application does not expect any access tokens yet. So let's change that. It's up to you where you want to ask for this token. In this case, I chose the service layer, which is then called by our web controllers. And before that, these functions just accepted the ID of an article and did their job in the database. But now they accept these access tokens, and if you look at it, I also implemented the principle of least privilege. because every function only requires the permission level that it's needed to perform the job. So the implementation is very trivial. They get the token as an argument, unwrap it, and unwrap it again to get the article ID, and then call the database with it. So it's literally just one more line for unwrapping the token. So this doesn't increase the complexity of your code base. The last place we have to change is our controller. So instead of calling our Boolean-based functions now and using if-else, we now call our new authorization functions on pattern match on this maybe. And if we got nothing, we return the 401 not authorized. And if we get a token, we can then pass it to the service layer where they do their job. And that's basically all there is to this. So at the end, we only added a few lines of code because you have to write some authorization logic anyway. We just added the wrapping and unwrapping into types. So we convert this basically to static guarantees that our compiler can enforce. And if you think about it, we use types here basically like other people are using signed tokens. So instead of using cryptography here, we are protected by the runtime of our language. By making the constructor private, making this module the only place where a value of this type can be created. It's like having access to some private key, signing some data, and the other functions then expect that this value is signed. In our case, it has to be of a certain type. And if we're still at it, let's stay for Haskell for the next example. Let's tackle injection in text now. We are using SQLite here as a database engine. It gets a connection to the database, asks the user for a product name, searches for it, and prints the found products. We use a simple database library here, so it's not a fully fledged ORM. And we have to write SQL by hand. So this sounds like this could be susceptible to some SQL injections. If you make the mistake of concatenating SQL queries with some user input, then you are owned. The solution to this are prepared statements, of course, but that's something you have to know and actively think about, actually. So what's the magic here? It's rather simple. An SQL query is not a string. It has the type query. It's not even a very sophisticated wrapper. It's just one type that gets wrapped around the string. And the relevant thing here is that all functions in this library expect that the function is called with something of type query. So this avoids the number one reason for SQL injections, mainly the accidental concatenation of queries with strings provided by the user, because queries and strings are not the same type, so they do not match. On line number 10, you can see that I explicitly call the SQL query constructor to convert this thing into the query. And performing a concatenation then would not be possible. The types are not matching. In this case, the wrapper even gets eliminated at compile time, so there's absolutely zero overhead of using this technique. Rust isn't the only language with zero cost abstractions. Now, Java again. It happens that we have to deal with data that can be considered as valuable or secret, and using them inside of our programs isn't usually a problem. But we have to be careful not to leak data to the outside. Our class contains a password hash of a user, so that's something we would like to keep to ourselves. And if you look at the ID thing here, that's another way to tackle this mixed ID problem. ID is a generic wrapper that just accepts any type. It doesn't do anything with it. It's just that you have a different representation on the type level, so you can't mix up things anymore. This pattern is also known as phantom types. To solve our data leak problem, we will use data transfer objects, so DTOs. Here I called it user view model to give it a more explaining name. And a DTO is a separate data type specifically made to be used for data exchange across boundaries. That's why we have to fall back to primitive types, because other applications and systems do not support our custom data types. When we create a DTO, we are in the mindset of returning only the necessities back to the caller. In this case, the caller doesn't need to know the internal ID of the user. We also know that the name is always displayed in full, so we can provide a computed property called full name here. We return the name, we return the date of birth, but as the datetime type and not our custom birth date type. And of course, the password hash stays with us. The user view model is also responsible for providing the methods to convert from and to the domain model, because the outside world is not a concern of our domain model. This makes it easy to change, for example, the serialization library without having to touch our core types. Get users could be a function in our controller. It calls the user service to get all users. At this stage, we will still have our domain user type. And then we map over this user list, converting into view models, calling this entity to view model function, and return those back to the caller. One benefit of using custom domain types is that as we are not using primitive types anymore, or basic data types, we have to provide some conversion function anyway. So might as well use the chance to prevent some security issues. Applying the reverse then solves the problem with mass assignment. So it's when an attacker provides more data fields than you expect, but your application is still processing them, like changing the role of a user, although only the name should be changed. To solve this, you explicitly create a DTO for the input data with only the fields that the client is supposed to change. Now we have cross-site scripting. Elm is a functional programming language, architecture, and framework for creating single-page applications. It transpiles to JavaScript and has the most friendly and useful compiler you will ever see. You write web frontends with Elm, so preventing cross-site scripting is like the #1 concern for them. And the solution is pretty similar to the one for the SQL injections. A web page is not an arbitrary string. It's HTML, which has some certain properties. You can only return web pages if they have the type HTML. There are a few functions that accept strings and convert them to HTML. Text is one of them. And all these functions perform output encoding and escaping, so JavaScript code does not get interpreted as code when displayed in HTML. Again, the compiler is forcing you here to pass your potentially dangerous input through a conversion function that takes out danger. You cannot forget to do this. The compiler is your friend here. And even JavaScript has more strict types now to implement this. They are called trusted types. And Lucas already showed us today how cool trusted types are. And if you want to learn more about them, you can also watch this great talk by Philippe in his last year's sec4dev video. You can scan the QR code or search for it later on. And now some of you may ask, does this work with all applications? And the answer is, in general, it depends. But there is one particular architecture that is for business applications that is rather well suited for this domain-driven approach. And it has many names. It's hexagonal architecture, onion architecture, clean architecture, also ports and adapters. And the functional approach is called pure core imperative shell. They all describe the same idea, that your business logic should stay in the core of your application, and your core does not depend on any external systems. All layers point inwards, dependency-wise, and the core provides interfaces which the outer layers then implement. So your rich domain types, they live in these inner two layers. It's validated and filled with business logic and protected from the outside impure world. In the outer layers, then, you provide your DTOs that crosses these boundaries and bridges the gap between your perfect world and the real world. They filter out all the nasty stuff, and so your business domain can work with good and well-structured data. This keeps you on the happy path and makes your most valuable code easier to maintain, extend, and understandable. At last, here are some book recommendations. So if you want to learn more about functional programming and domain modeling, I can highly recommend this book by Scott Blashin. I've read it multiple times, and it's a great source for ideas and that will your program life just easier. The examples are all in F#, but the lessons you will learn are valuable in all languages. And for the object-oriented programmers here, there's this implementing domain-driven design by Vaughan Vernon, which is a modern take on the Blue Book, also called the Red Book. Who would have thought? So, the key takeaways: make a legal state unrepresentable, less tests to write, less bugs to experience. Encode business rules in your types, guide other programmers by designing your types and functions in a way that makes it obvious how to use them and what to expect. Parse, don't validate. There's actually a nice blog post with that same title. If you perform any kind of validation in your project, embed that knowledge by putting it in some type. Boolean checks are ephemeral. Once you leave the branches, there's no proof that you ever performed any kind of validation. Use the compiler to your advantage. Let it prevent you from doing stupid mistakes. Using rich domain types basically lets the compiler do all the work for you and write free tests. It makes sure that you cannot call functions with invalid data. Tests for free. Don't miss this offer. And last but not least, eliminate security vulnerabilities by design. You get great security when it's the default and you have to do extra stuff to shoot yourself in the foot. And with this, we're done. Thank you for listening. And I'm happy to answer all your questions now.
Thank you, Michael, for this really, really cool presentation. We've got a few questions. The first one, I think you already half answered it. It is about recommendation resources for implementing your concepts in various languages. We represented 2 books, which are probably a good recommendation already. Do you have some blogs or other internet sources?
So about all this, the domain-driven approach, Microsoft is releasing a lot of resources for that, and there are demo repositories. Most of the stuff is in C#, and they always try to implement this idea of modeling your domain very explicitly and avoiding security issues with it.
Yeah, sorry, I was just reading. Should such design models not be taught to students or people that are learning programming and coding?
I try. So maybe I will do a teaching career and start doing that, actually. But yeah, so one quote from Uncle Bob, I think many of you know him, is that every 5 years, the numbers of programmers is doubling. So we all the time have at least half of all programmers with less than 5 years of experience. So only teaching them is maybe not the right approach, because we always have juniors and we can't always teach all these techniques to them. So I guess it's some mixture of providing good tools and frameworks which just do their job so you don't have to know about it. But then, of course, teaching it is also the next valuable thing.
Thank you. Do you know of any well-known frameworks or, wait, it jumped. Do you know of any well-known frameworks or libraries that already embrace these concepts, and how battle-tested are those ideas? Or is this idea?
Yeah, like in the JavaScript world, we have all these front-end frameworks that now applying these techniques to prevent cross-site scripting, like we have heard. Then it really depends on the language. So in the Haskell world, it's very common to put as much as possible into the type level to get all these guarantees. You even have then type-safe APIs and routes, so you can't call endpoint with the wrong URL, for example. And the other languages are now catching up, I guess. They now provide all the required features like sum types and pattern matching that makes it very easy to use these techniques. So I guess I've seen there is some strongly typed ID library for C#, for example. So I think this thing is now catching on.
And what are the most important lessons you have learned from applying DDD?
It just makes way more sense for me. I've seen so many projects where the logic and basically that's what your application is really about, because just integrating some external libraries. That's like everyone is using that. The business logic is that what differentiates between you and your other enemies, basically. And splitting that up and distributing it across the whole code base, it's not maintainable and it's not reliable. So if you apply all these techniques and have this really clear structure, then it just makes more fun to program, actually.
Perfect. Another question, actually, from my side. F# is like now I hear more and more about F#, and it's going to be a cool language used. Do you think F# is also a language which?
F# is cool, yeah.
Yeah.
So basically, so F# is I think 15 years old now, and every feature in C# in the last 10 years comes from F#, and everything in F# comes from Haskell. And basically, all the newer versions, newer languages like Rust. Rust is heavily inspired by OCaml, and F# is Microsoft's version of OCaml. So you have this tree of languages which are so filled with great ideas that we just don't have in our mainstream languages, although they all trace back to ML from the 70s. So we had all this stuff for decades now, but the industry is just catching up now.
Another question is, does type-driven domain design provide any other benefits besides avoiding some pitfalls, e.g. null pointer exception?
Yeah, so if you use concrete terms and put it and use words that other people that are not programmers can also understand, you can basically write your documentation with it. So your code and the documentation is the same thing. So they can't get out, as the documentation can't get outdated anymore. And if you write it on a high level, which you can do, then it's basically readable for every person involved in the project. So that's also a very helpful thing. And just introducing new juniors to the project, they can just follow the types because there's no other way to call these functions. So it's just a really good guardrail to really push you into the right direction.
Thank you. Can you recommend some languages that make it easy to implement these principles? I mean, like we had.
What?
Or can you recommend some languages that make it easy to implement these principles? So
yeah, the languages that I listed. So if you really want to be super cool, then you use Haskell, of course. But F#, like I mentioned, super easy to integrate into existing projects. In the JVM world, you have Scala and Clojure, for example, although Clojure is more on the dynamic side, but they also use the right techniques by choosing the right data structures to avoid issues. And in the web world, yeah, now we have the trusted types, but there's also Elm or Rescript, which is Facebook's version of OCaml for the web. So yeah, the things are repeating all the time, and now we get all this cool stuff that is known for decades, actually.
Thank you very much. Again, a warm applause.
Thanks, yeah.